This is the second video in a series about simple electronic devices. We'll look at variable resistors and potentiometers. Consider the simple circuit shown here. We have a battery or a constant voltage source and two resistors in series, RA and RB. Since they are in series, Ohm's law tells us that the current will be controlled by the sum of the two resistances. Solving for the current, we have I equals V divided by RA plus RB. The voltage represents an energy drop across this resistor. In a way, it is similar to the change in energy for a river going over a waterfall. Imagine a cascade of two levels for this river. The potential energy for this river is proportional to its height. As the water flows from the top to the middle level, it loses the energy corresponding to this drop in height. The water still can drop this distance and deliver a proportional amount of energy. That's analogous to the current in our circuit. Energy, or voltage, is spent in driving current through each resistor. The energy dropped going through the first resistor is the current times the resistance, or I times RA. At this point, there's still voltage to be dropped across the resistor RB. Again, that energy can be calculated from the current times the resistance, or I times RB. Let's try a calculation. Let the total voltage, or the battery voltage, be 10 volts. We'll set RA to 1 kiloohm, or 1,000 ohms, and RB to 3 kiloohms, or 3,000 ohms. First, let's calculate the current. It's the same throughout the loop. It's equal to the total voltage divided by the total resistance. That's 10 volts for the battery divided by 1 kiloohm for RA and 3 kiloohms for RB. We'll multiply by 1,000 to convert from kiloohms to ohms. The result is 2.50 times 10 to the minus third amps, or 2.5 milliamps. The voltage measured on the meter, that is the voltage drop across the resistor RB, is the product of the current and RB, or 2.5 times 10 to the minus 3 amps times 3.00 times 10 to the third ohms, or 7.5 volts. Let's step back a moment and generalize about this result. The energy at the top of the pair of resistors is 10 volts. Some is lost in pushing the current through the first resistor, and our meter is set to measure the energy used in driving current through the bottom resistor. We can calculate the voltage by multiplying the current in amps times the resistance RB. The current is the ratio of the total voltage dropped across the pair of resistors divided by the sum of the resistances. Then we multiply by the resistance over which we are measuring the voltage drop. I'm going to rearrange terms here to group the resistances together. This ratio of resistances gives the fraction of the total resistance represented by RB. And the product of this fraction and the total voltage dropped over the pair of resistors yields the voltage drop for the current going through RB. To put it another way, this ratio of resistances equals the fraction of the total voltage represented by the measured voltage. This provides a practical way of dividing a voltage down. We call this a voltage divider. This tells us that we can set up a circuit to select any voltage that we like between 0 and 10 volts, or 0 in the total voltage, by choosing the appropriate resistors that give us the target fraction. For example, let's start with our 10-volt battery again, and imagine that we want a voltage of 6 volts. We have our two resistors in series again. Now our goal, though, is to choose a pair of resistors that will give us a meter reading of 6.0 volts. So our task is to find appropriate values of RA and RB. First, we need to find the fraction of the total voltage represented by 6 volts. So we take the ratio of 6 volts over the total voltage of 10 volts, and we find that to be equal to 0.600. That should also be the ratio of the resistances RB to the sum RA plus RB. Since there are still two variables here to determine, let's impose another relationship or another restriction. Let's imagine that we want to keep the current small so we don't drain the battery very much. Let's assume that we're going to restrict the current to 1 milliamp, or 1 times 10 to the minus third amps. That lets us calculate the total resistance from the ratio of V total over the current I. Here we have 10 volts at the top of the resistors and 1 times 10 to the minus 3 amps in the denominator. That's numerically equal to 10 kiloohms or 10,000 ohms. So the sum RA plus RB equals 10,000 ohms. Our fraction of 0.600 is the ratio of RB over 10,000 ohms. By rearranging, we get that RB is equal to the product of 0.6 times 10,000, or 6,000 ohms. And RA is just the difference between our total, 10,000, and the 6,000 ohms, or 4,000 ohms. Now you should be able to try one of these on your own. Pause the video and calculate suitable values for RA and RB. Here you can check your answers with the values that I get. There are many situations where it's very useful to use a voltage divider to generate or create a specific voltage or even vary the voltage at will. Using resistors with fixed resistance values is very awkward if we want to make changes easily. This diagram represents another device that lets us do that conveniently. This is called a variable resistor. Notice that it has 3 leads. 2 represent the 2 distant leads of a pair of resistors connected in series. The third lead is connected to a sliding contact. Its position is adjustable. Here is a commercial variable resistor. The contact in the bottom left is attached to the sliding wire that moves when we turn the shaft. I've opened up an old device so that you can look inside. The sliding contact is hanging out in this photo. You can also see the coil inside the housing. This coil is made up of a resistive material with a resistance that increases with length. The contact is designed to slide along the coil as we rotate the shaft. As the sliding contact spirals down the coil, the resistance between the contact and the end of the coil nearer us increases. So the contact represented by the arrow in this diagram changes distance between the 2 ends, one distance increasing while the other decreases, and the resistance between the pointer and either end changes in proportion. Commercial variable resistors are available in a wide range of total resistance values, physical sizes, and in the number of turns that it takes to move the slider between opposite ends. These are very convenient for voltage dividers. Here I'm using a very tiny adjustable resistor to select voltages from a flashlight battery. Although this device is nice and compact, it goes from one extreme to the other in less than a whole turn. Here is how we would diagram this circuit. When a variable resistor is used in this way to provide a selectable voltage, it is called a potentiometer, since we are metering out a potential energy or voltage value.